Hello everyone, welcome to today's talk. Today we'll be talking about how combinatorics and flow networks sort of intersect and sort of look at the connections between these two. Right, so I guess I'll kind of start with a little bit of an introduction to like who I am. So my name is Vero. I am a 6th year doing computer science and math. And my specialization is in algorithm design, number theory, combinatorics, graph theory, and computational complexity theory. So I do a lot of the theoretical computer science stuff. Alright, let's get started. So for the way that today's talk is going to be structured, we're going to briefly look over some basic ideas of maximum flow, and then we're going to get into sort of the main results. We're going to be looking at Hall's-Maris theorem, Dilworth theorem, and we'll end it off with Menger's theorem. So, what is flow? What is a flow network? So, crudely speaking, imagine that you have a directed graph, and you have sort of two vertices that you sort of want to look at. So, the first vertex is a source, and the second vertex is a sink. And the question here is, imagine that I have an infinite supply of water starting from the source, and I want to basically transport the water along these sort of vertices into a town, and the town is going to be the sink. And the question here is, if I have an infinite supply of water to begin with, how much water can I push through all of these pipes so that I get to the town? And I want to maximize the amount of water, or amount of flow, to the town. So that's the question that we're going to recover in today's talk. So kind of to illustrate what's happening here, each of the numbers here represent the capacity of the pipe. So one thing that we don't want to do is to burst any of the pipes. So we don't want to push too much water into each of the pipes so that the pipes explode. So we can supply up to whatever is whatever the capacity of your pipes are. So, given a flow network then, the question here is how much flow can we actually send from S to T? So, given that I have an infinite supply of water to begin with in S, and I want to transport it all the way to T, well, what we can do here is to say, okay, well, if I start at S, I can transport 2 units of flow to U, and then I can go from U to X by transporting all of the flow from U to X. And then I can go from X to T with 2 units of flow. Likewise, I can go from S to V with 5 units of flow, and then I can sort of transport it into 2 different directions. I can transport it up from V to X with 3 units of flow, and V to Y with 2 units of flow. So from X then, I have 2 units of flow from U, and 3 units of flow from V. And then what I can do is from X, I have 5 units of flow, and I can send all 5 to T. Likewise, for V, I have 2 units of flow, I can send it to Y. Y would only have 2 units of flow, and I will send it to T. So I can see that the maximum amount of flow I can send from S happens to be 7. And if you try doing any other combination, you'll find that it will be equally as good or worse. So the question here is, if we know the problem that we want to solve, how could we solve it? And then, there are a couple of ways we can do this. One way is to basically try as many paths as possible. But what we'll find is that if we arbitrarily choose the paths that we want to take, then we might hit a point where we can't send any more flow when there's actually a possibility that we can actually send more. And we'll look at an example later on as well. So one thing we could do is to try as many paths as possible. One way to do this is to go, okay, well, if I need to start at the source and I want to end at the sink, then I want to basically find all of the ST paths, so all the paths that start at the source and end at the sink. And I want to send flow down that path. And then what we're going to do is we're going to keep updating all the flows and capacity that we send along the way as well. So we'll have a look at this example here to sort of illustrate what's happening. So if we try to pick a random path, one path that we can pick is this sort of zigzag path. So one thing we can do is to send 3 units of flow from S to U, and then 3 units of flow from U to V, and then 3 units of flow from V to T. And what we'll find here is that if we try any other path, it's not possible, right? Because we basically used up all of the flow that we have, right? We can go from S to U, but then we can't send any flow from U to T because there's actually no more amount of water I have in U because we've consumed all that when we move to V. But the thing is though, can we actually do better? And it might seem hard to suspect at first, but it turns out we can actually do better. If we take these two paths instead, so going from S to U and then U to T, then we send two units of flow to T, but then what we can do is we can send 1 unit of flow from U to V, and then we can send all of the remaining flow from V to T. And you'll find that this will give you a flow of 5, right? Because you can send 2 units of flow from U to T, and then 3 units of flow from V to T. So the question here is like, okay, we started off with the original path that we chose. And we said, well, okay, the flow was 3, but what went wrong here? So the issue here is that we arbitrarily picked a path from S to T, and we sort of said, okay, this is a path that we're going to take. But what happened was that all of the other paths that were possible was actually blocked out because either U has no more flow or V has no more flow. And as a result, we couldn't actually have any more paths from S to T. So one way to kind of fix this then is to say, okay, if we need to figure out a way to fix our mistake, then we need a way to undo a flow that we've previously produced. So one way to do this is to say, okay, if I have a certain amount of flow that I've sent, then what I can do is I can keep track of the amount of flow that I can send back. And by doing this, I can just keep updating each of the capacities, and we can try to find more paths along this way as well. All right, so let's have a look at this original example that we had. And let's start with our original problem. So what we're going to do is we're going to send the flow from S to U, from U to V, and then V to T. And what we found here was that there were no more augmenting paths because all the augmenting paths would have been consumed. Okay. So what we can do here then is to say, okay, because there are no more augmenting paths, I can send some of the flow back. And the way to do this is to say, okay, well, starting from T, I go to V, and I can send back, I can send it back up to 3 units of flow. But really, I only need to send back 2 units of flow. So I'm going to only send back 2 units of flow. From V to U, I can send back 2 units of flow. And now, what I have here is I have a vertex that has 2 units of flow available. And what we can do is we can find another augmenting path or ST path such that we get another path possible here. So once we have this, then we update all of our capacities. So notice that the U to V path only has 1 unit of flow left because we sent all of that. We sent 2 units of flow back. Likewise, from V to T, we sent 2 units of flow back. So we only have one. We only have a flow of 1 left in this along this edge. And what we can do here is to say, okay, well, we have another augmenting path now from S to V, and then we can send 1 additional flow from V to T as well. Now what you'll find here is that pretty much all of the possible augmenting paths are filled up. Therefore, there are no more paths possible, and this is going to be the maximum flow that we can have. So we terminate with a maximum flow of 5. And this is essentially what the algorithm is trying to do. It's saying, okay, arbitrarily pick a path, and then once you arbitrarily pick a path, then you're going to keep updating all of our backward edges so that maybe there is a way to find better or to find new paths from S to T. Alright, so there are some kind of notes about the four-Fulkerson algorithm. So notice that the first thing is that the algorithm must terminate because there are only finitely many paths and there are only finite amount of flow that we can send. So therefore, the algorithm itself must terminate. And we can reuse all of the edges, and when we do that, we have to send flow back to find better ST paths. And then the final output is basically a set of saturated edges, which also correspond to the edges that are used along the maximum flow of our flow network. And the running time for this algorithm is the number of edges times the amount of flow in the graph. There are other algorithms out there. So Edwin's CARP is a special modification where instead of choosing an arbitrary path, you instead start by choosing the path of shortest length. And it turns out that in some graphs, it actually runs a lot better. There's also Dinnick's algorithm, which basically looks at blocking flows and pre-flow push, which is sort of the standard in modern flow networks. All right, so now we're going to get to the really interesting results. So we've sort of had a look at flow networks, what they were. We had a look at some algorithms that run in polynomial time. Now we're going to have a look at some of the applications of flow networks. So the first thing we want to look at is a cut. So the idea of a cut is to basically separate your graph into two parts. And what we're going to do is we're going to separate it in a way where the source is on one side and the sink is on another side. And the reason for this is because, well, we're interested in, well, maybe the number of edges that are needed to completely separate the source and the sink. And it turns out this is a very special a very important concept, and it pops up in what we call the maximum flow minimum cut here. So formally speaking, a cut is really just a partition of vertices, such that if you take the union of the two partitions, you get exactly the original vertices. If you take the intersection, then it's an empty set, and the source has to be on one side, and the sink has to be on one side. So the cut basically splits the graph into two parts. S and T are going to be completely separated. And we're going to define the capacity of the cut to be the sum of the capacity of the edges that basically pass through the cut. And we're only going to do this in the forward direction, so we're not going to count any of the edges that are sort of face backwards. So the starting vertex is in T, and the ending vertex is in S. So we're not going to count those edges, we're only going to count edges along the forward direction. So here, you can kind of see that there are, technically speaking, three edges that pass through the minimum cut. But what you'll find is that one of them is facing the wrong way, so we don't count that. Instead, we count only the 4 and the 2, and that's going to be it's going to be a cut. It might not necessarily be the minimum cut, but it's just going to be some cut. All right, so we're going to get to one of the interesting results in this talk. So the first theorem, the big theorem that we're going to look at is called the maximum flow minimum cut theorem. And this theorem basically says, if I have a maximum flow of a flow network, that actually corresponds to what we call the minimum cut of the same flow network. And really what that means is that if you can find the maximum flow, you can also find the cut with the minimum capacity. A way to kind of think about this is that the minimum cut tells you, it limits you to the amount of flow that you can send along the edges that you must pass through when you're performing a maximum flow. So when you're performing a maximum flow, you're going through a lot of these edges, and there are some edges that you have to cross. That's going to basically be the minimum cut, and that's going to basically be your bottleneck for the maximum flow. The maximum flow tells you that you have to send flow along these edges, because these edges are the edges that completely separate your source from the sink. So you have to actually pass through those particular edges when you're performing your maximum flow. And so therefore, you can kind of see that if you put these together, the minimum cut, the capacity of the minimum cut corresponds to the maximum flow. So that was the sort of the introduction. Now we're going to get to the really interesting results here. Does anyone have any questions before we sort of proceed?
Still don't understand what the max, minimum, cut, maximum.
Yep. So the idea with the maximum flow is that you sort of have an algorithm to determine what the maximum flow is, right? Where you sort of go through all of these edges, and then the result is, well, how much flow I can send from S to T, right? The minimum cut says, okay, I want to completely separate my graph into two parts, into two partitions. And I want to do this by crossing the edges such that the sum of my capacities are minimized, right? So I will cut through some of the edges, and then the idea is that, well, if I cross through some of the edges, they're going to cross through they're going to cross the edges with some weight, and I'm going to sum over all of that weight. Now the intuition behind this theorem is basically saying that the minimum cut tells you the actual bottleneck of your maximum flow, because you have to send all of the flow along these edges when you're performing your maximum flow. Now, the minimum cut will tell me exactly how much flow I can actually send along these edges, because there could be some paths that I can take that have a wider capacity, but along the way I have to pass through all of these edges, right? And as a result, because I have to pass through all of these edges, and these are edges of the sum is minimal weight, that means the maximum flow is limited by all of the weights along these particular edges along my curve.
Confused during what we undo.
Yep.
That's like what makes the amount of we undo better.
Okay, so remember that when we're arbitrarily choosing the paths, it doesn't matter how we choose the paths, right? We can choose it however we want, but there could be some cases where once we choose a particular path, that actually limits the amount of, or the paths that we can actually choose along the way. Now what the undoing process does is that it says, okay, well, I have a path that I've chosen. Once I choose the path, what I want to do is I want to say, okay, if I can undo all of these operations, can I find a new path that might be some of these capacities, such that I get a better maximum flow, or I get a better flow in the end. So the undoing operation will tell you, I want to basically backtrack to a place where I was probably most comfortable with. And by undoing all of these operations, I can find new paths that I probably would not have been able to if I chose this path to begin with, right? Because once I choose this path, it's basically a path that I can't really touch. But once I touch it, then I can probably undo it so that that there are some paths that I could have actually crossed, I could have actually used when that wasn't even consideration in the first place.
So like we learn to undo it because there's no other way to get to that.
Yeah. So once we have this path, there was no other way to get to T. But what we can do is we can see that there were actually some other augmenting paths that were possible. So what we're going to do is we're going to undo the process so that we can try out all of these other paths as well. And once we have that, then we will be able to tell out of all of the paths that we've chosen, which one's going to maximize the amount of flow that we send.
You just have to try it.
Yeah. So you keep trying all of the augmenting paths until there are no more left. And once you have no more left, that will tell you what the maximum flow is going to be. Are there any other questions before we proceed? Yeah. right? So you can kind of see the process here is that we're undoing two edges. And then once we undo the edges, we can see that from S to U, we were able to send another 2 units of flow to T. And all of the other edges will keep their new capacities or new flow. And then we'll have a final maximum flow. Cool. All right, so this is where the fun begins. We're going to look at 3 special theorems. All of them are sort of kind of unrelated to each other, but also related in some way. And we're going to see how they're related to maximum flow. So the general structure for a lot of the theorems that we're going to look at is that, well, the maximum of some quantity corresponds to the minimum of another quantity. And you can kind of see that this is also the same with your maximum flow min cut theorem. The maximum flow corresponds to the minimum cut. So let's have a look at the first theorem. So this theorem is Hall's marriage theorem, and we're going to explain why it's called marriage theorem in a second. So for this one, you're not really given a graph. You're sort of given a family of sets. You're given a collection of sets. And the idea is that you sort of say, okay, I choose a subset of these sets, or I choose a subset of these elements that belong to at least one of your sets in the family. And we're going to define a term called a transversal. And a transversal, you can kind of think of it as just a cross-section of my family. What I'm going to do is I'm going to take a subset of my family, and what I'm going to do is I'm going to pick one element from each of these sets. And it turns out that this will exist if and only if it satisfies a certain condition. And this is exactly Hall's marriage theorem. So one way to kind of think about this, right, is to say, so one way to kind of think about this is to say, okay, I have a collection of these sets. I have a collection, and I say, okay, for each of my sets, I'm going to choose a particular value, or choose a particular element that comes from my comes from my set. And the question here is, well, because some of them can overlap, is it possible to actually do this such that each of the elements that I pick is unique? And it turns out this is true if and only if you basically have enough elements in your set to begin with. So when does this sort of transversal set exist? So what we're going to do is we're going to just consider just a sub-collection. We're just going to consider a subset of the sets in my family. And what I'm going to do is, well, maybe the first attempt we're going to say is, okay, well, we're going to assign an element from S. So remember, S was my subset, so that's my transversal. We're going to assign an element from S to represent a set in G. And the question here is, well, is that even possible? Because remember, S was a subset of the union of all of the elements that belong to at least one element in F. The issue here is that if I only choose it from S, if I only choose elements from S, then, well, you might accidentally choose an element that doesn't actually exist in any of my sets, right? Because I could choose, say, X, Z, and then I could accidentally choose B, which doesn't belong in any of my sets. So as a result, it seems like just choosing it from S is not enough. It's too loose of a condition such that a transversal would exist. So we need to think of something a little bit stronger than just choosing it from S or from my transversal. So let's sort of try again then. So instead of choosing it from maybe a subset of the union of all of my elements, maybe I want to restrict the elements to specifically the elements along my family. So what I'm going to do is I'm going to say, well, I'm going to denote Y to be the set of elements that belong to at least one of my sets in my sub-collection G. now what I'm going to do is I'm going to assign an element from Y to represent a set G. So this is effectively the same as what we did before, but instead of looking at the union of all of my elements, I'm going to restrict it to only looking at elements that belong to at least one of my sets in G. So now I know for sure that whatever I pick in Y has to come from one of the sets. But there's still an issue here. Even though we have limited our choice of elements, the issue here is that what if we don't actually have enough elements to choose? What if instead of choosing distinct elements, what if we actually choose one element to represent multiple sets? So what we want to do is now to place a condition on maybe the size of Y, such that a transversal is always guaranteed to exist. So one easy way to do this, one easy way to say, okay, I will say a transversal exists is, well, I need to have enough elements to begin with, right? So for each of my sets, I need to have, well, at least one of my elements to be in my set. So therefore, what I need to do is I need to have the size of my family, so the number of sets in my subfamily, has to be at most the number of elements that I can actually choose. That seems like a pretty good restriction. Let's have a look. And it turns out that this is actually a sufficient and necessary condition for a transversal to exist in the first place. And we can write Y to be, well, the union of all of the elements in my set G. And this has to hold for every subcollection G that appears here. So this has to hold for every subcollection or subfamily. And this is basically our theorem. So Hall's marriage theorem basically tells me that if I have a finite, or if I have a family of finite sets, then my family F will have a transversal precisely when for every single subcollection that exists, the size of G has to be at most the union of all of my elements in my set. And we'll see how maximum flow plays into this. All right, but to do this, we sort of need to reformulate Hall's marriage theorem a little bit, because at the moment, we're just working with sets. We're working with a family of sets. So what we need to do is we need to reformulate it in a way where maybe we can actually get some information out of maximum flow and minimum time. So what we want to do is we might want to just represent this as a graph. How could we represent this as a graph? Well, one easy way to do this is to say, okay, every single set in F will represent a woman, and a woman will have a list of men that they want to marry, right? So you can kind of think of it as, well, the elements inside of the set of F is going to be the men that the women are okay to marry. And an edge between two vertices is possible precisely when they can be married, so they're okay to be married. So a woman will have a collection, or will have a list of men that they might want to marry, and then an edge will represent that they can get married, or it is possible for them to be married. So what Hall's marriage theorem is basically saying is, for any collection of women, we essentially need enough men for each of the women. And what you can kind of imagine here is that it forms a bipartite graph. And we'll have a look at the formulation in the next slide. So imagine that this is my family. My family has A1, A2, A3, A4. There are 4 sets in my family. And A1 is going to be ABC, A2 is A, A3 is CD, and A4 is CD. What we want to do is we want to convert this into the graph. So the way that we're going to do this is each of the sets are going to represent a vertex, and each of the elements A, B, C, and D are also going to represent a vertex. And what we're going to say is, well, A1 has to be connected to A, B, and C, the vertices representing A, B, and C. A2 has to be connected to the vertex representing A. A3 has to be connected to the vertex representing CD, and likewise with A4. So let's have a look and see what the graph here looks like. So this is effectively what the graph looks like. And I also highlighted the matching as well. Right? So what you can see here is that A1 is connected to A, is connected to B, and also connected to C. A2 is only connected to A. A3 is connected to C and D, and A4 is connected to C and D as well. And what I've done is I've just highlighted A1 representing, or B represents A1, A represents A2, C represents A3, and D represents A4. And this corresponds to this matching here as well. So now we have a one-to-one correspondence between the family of set version of Hall's-Marriott theorem and the graph theoretic version of Hall's-Marriott theorem. So now what we want to do is we might want to just look at the graph version of Hall's-Marriott theorem and maybe play around with that a little bit. Okay. So this is the graph formulation of Hall's-Marriott theorem, and to just simplify things a little bit, what I'm going to do is I'm going to suppose that the vertex set of V1 and the vertex set of V2 are equal, just to make things a little bit easier to visualize. But in the more general case, this is not necessarily, you don't necessarily need them to be equal. So, the formal theorem for the graph theory version is effectively the same. You sort of have a bipartite graph, and it turns out that G has a perfect matching if and only if the size of S is at most the neighbor set of S. So S is a subset of my vertices of V1, and basically what's happening is that I need enough neighbors for each of my sets in S, and this is essentially the graph theory version of Hall's-Marriott theorem. All right, so now we're going to see sort of a demonstration of how the maximum flow min-cut theorem implies Hall's-Marriott theorem. So suppose I have this graph that we saw before. What I'm going to do is I'm going to just direct all of the edges. And once we direct all of the edges, then I'm going to have two special vertices. And these special vertices are going to represent the source and the sink. From the source, I'm going to connect it to all of my vertices on the left, and the sink is going to be connected to all of the vertices on the right. And each of these edges are going to have capacity 1. What about the capacity of all of the original edges? Turns out these are going to have infinite capacity. So they're not going to have capacity of 1, they're going to have infinite capacity. And the reason for this is because if I want to apply the minimum cut, I want to ensure that the minimum cut doesn't actually cut through any of these edges here. And if I apply my minimum cut, then I'm going to get a minimum cut of 4. If you apply the maximum flow, then you're going to get a maximum flow of 4. That's going to represent the minimum cut of 4 as well. Ooh. And if you interpret this as well, this will tell me that there are 4 vertices on the left-hand side that can be matched. And this will tell me that there is a perfect matching because each of my vertices on the left can be matched. Okay, so some notes about this construction. Edges that cross the minimum cut can't actually come from edges that start from a red vertex and end with a blue vertex, because each of those have infinite capacity. So any of the edges that cross my minimum cut can only occur from either the red side or the blue side, but they can't cross along, they can't cross from red to blue. So what I'm going to do then is I'm going to take some subset of V1, and what I'm going to do is I'm going to look at all of the neighbors of S. Notice that the neighbors of S can only belong to the blue vertices, and it has to only be neighbors to at least one vertex, one set or one vertex in S. And what we'll want to do is we want to only consider vertices. If we only consider those vertices themselves, then the maximum flow will tell me exactly which vertices are going to be matched. And if those vertices are going to be matched, then I need to have as many neighbors as I have sets. And so you can kind of see here, for example, if this was my subset, so if I only consider this and the first and the third, the fourth vertex, then this is sort of the construction that I have here. So I only consider these vertices, and what you'll notice is that you'll have a minimum or maximum flow of 2. Each of these vertices are going to be matched as well. And that's exactly what Hall's marriage theorem tells me. So here we're going to look at sort of 2 examples of graphs. On the left-hand side, you'll have a bipartite graph that satisfies Hall's condition. So for every subset of vertices on the left, there are enough neighbors. And so you can kind of see that there is going to be a perfect matching if you just follow along some of the vertices on the left and the right. But what you'll notice is that on the right-hand side, you don't actually have a perfect matching. Because if you look at these 2 panels, these 2 sets here, what you'll notice is that they are only connected to one vertex. And so if you're trying to find a perfect matching, only one of these vertices will be matched. You can't have both of the vertices matched. And so therefore, this, on the right-hand side, this doesn't satisfy Hall's condition, and you can see that this also does not have a perfect matching. Whereas the one on the left-hand side has a perfect matching, and you can also see that it satisfies Hall's condition. So this is a way to relate Hall's marriage theorem to max flow min cut. So that was the first theorem. The second theorem is a bit more interesting. So this one, we're going to look at a finite partially ordered set. So if you're unfamiliar with a partially ordered set, it's really just a set of objects with a binary relation that satisfies 3 conditions. So the first one is reflexivity. So every element must be related to itself. Anti-symmetry, so you can't have that one thing is connected to another thing, and also if x is related to y, then y can't be related to x unless x and y happen to be the same. So you can only have either x being related to y or y being related to x. You can't have both. And transitivity. So if x is related to y is related to z, then x has to be related to z. So that's the basics of transitivity. So now we're going to look at these sort of combinatorial objects. So the first thing we're going to look at is what we call a chain. So if I had a partially ordered set, what I can do is I can sort of look at the connections between these sort of objects. So P is going to be a finite partially ordered set. We're going to denote a chain to be a subset of P, which is sort of a set of objects, such that if I take any 2 points, if I take any 2 elements in my chain, they have to be comparable in some way. And we sort of define comparable by, well, there has to be a relation between x and y, or y and x. So for any 2 elements, x and y, they have to be related. So you can kind of see here, if I only consider the red points, all of these points are going to be related to one another. The first point is going to be related to the second point is going to be related to the third point, and the first and the third points are going to be related. And likewise, I also have that the first point is related to the second point, and the second point is related to the third point, so to the black point, and so the first and the third, first and the black point are also going to be related. So here you can see that you'll have two chains, one being the completely red chain, and the other one being the red, red, and then black chain as well. All right, so once we have that, then we'll also define anti-chains, and then we'll look at how these two things are related. So instead of a chain where two things are comparable, now we're going to look at sort of the antithesis of chains, which are anti-chains. So for anti-chains, these two things, if you take any 2 points in your anti-chain, they're completely incomparable. You cannot actually compare them to one another. So you can see here, in this example here, you'll find that the far right red point and the black point are completely incomparable. There's no way to compare between these two points. So it turns out that there is indeed there is actually a nice connection between chains and antichains. In particular, the size of an antichain, or the largest size of an antichain, corresponds to the number of, or the smallest number of chains required to completely cover your partially ordered set. And we will see why that's true. So if I look at this example here, then, well, there are a couple of things that we can note. The first thing is that, well, if I take 2, 4, 12, that forms a chain. Everything inside of my chain, all of the elements inside of my chain are completely comparable. But also, 3 and 6 are also comparable. So these two things form a chain, and then they completely partition my actual set. So these two things form a chain, and this chain completely covers all of the points inside of my chain. But what you can see here is that if I take 4 and 6, these two things are completely incomparable. You can't compare 4, and you can't compare 4 to 6. So this will form an anti-chain, and what you'll find is that there's actually there's a couple of anti-chains you can choose. You can choose 2 and 3 as well, but you can't choose any anti-chain that's larger than 2. So here, interestingly, there are 2 chains that completely cover my set, and there's also 2 anti-chains. Or there's actually an anti-chain of size 2. So you can see that in this example here, the theorem holds, and the theorem holds more generally for any partially ordered set. All right, so let's go through Dilworth's theorem. So suppose I have a collection of disjoint sets that completely partition P, and suppose that C is the smallest collection of chains. And we're going to also denote A to be the largest chain of P. It turns out that the size of A, so the largest size of the largest antichain, corresponds to the number of smallest number of chains that completely partition your set. Okay. Now what we're going to do is we're going to reformulate the theorem. So what we're going to do is, remember that with Dilworth's theorem, we have just a set of objects, and we have some sort of relation on these sets, or on these objects. So what we're going to denote is that every single point inside of my set is going to be partitioned into 2 separate vertices. We're going to call it P minus and P plus. If 2 things are related, so if you take 2 distinct objects and they happen to be related, we're going to draw an edge with capacity 1 from the first point with a minus sign to the second point with a plus sign. And then we're going to also add sort of additional source and sink vertices along the way as well. So if I started off with this partially ordered set, this is going to be the flow network that I'm going to get in the end. Every single edge will have capacity 1, and I've also just color-coded them just to make things a little bit nicer to look at. So notice that 2 is related to 4, 6, and 12. So 2 is related to 4, 6, and 12. So the edge from 2 minus will be connected to 4 plus, 6 plus, and 12 plus. Likewise, 3 is related to 6 and 12. So 3 minus is going to be connected to 6 plus and 12 plus. And you can kind of follow the same pattern here as well. So this is going to be the flow network I'm going to construct out of my diagram of my partially ordered set. And what we can see here is that by our original inspection that we had before, we had 2 chains for our partially ordered set. This is going to be the corresponding flow that we're going to construct. So notice that there is a chain from 2 to 4 to 12. So what I'm going to do is I'm going to saturate the edge from my source to 2 minus, and then from 2 minus to 4 plus. That represents that we're considering this edge here. And then from 4 plus, we're going to go straight to the sink. Now, from 4 plus though, we know that there is going to be an edge from 4 to 12 in my chain. So on my flow network, I'm going to have an edge I'm going to have a saturated edge from 4 minus to 12 plus, and that will represent this edge here along my chain. And likewise, if I consider just the 3 to 6, then that's going to correspond to the blue edge here. So I'm going to go from the source to 3 minus. From 3 minus, I'm going to go to 6 plus, and I'm going to go straight to the sink. And what you'll find here is that this is going to be the maximum flow of my flow network. And by my maximum flow, that corresponds to the number of chains that I have in my partial order set. So we're going to sort of explicitly look at the relationship between these two. So we're going to denote F to be the maximum flow of the flow network. What we're going to do is we notice that P is going to be partitioned into, well, it's P minus F chains. To see this, notice that P is really just the number of objects that I have to begin with. So I have 5 objects. The maximum flow that I'm going to get is 3. And so that means P is going to be partitioned into 2 chains, right? And the 2 chains that I'm going to get in the end come from the fact that we know we can go from S to 2 minus, 2 minus to 4 plus, 4 plus to 4 minus, 4 minus to 12 plus, and then 12 plus to T, which corresponds to my chain 2, 4, 12. And likewise, I can go from S to 3 minus to 6 plus, and then to T. So my partially ordered set P is going to be partitioned into P minus F chains. And notice that if I have a maximum flow, that means that B is going to be minimized, right? Because the maximum, if F is my maximum, then P minus F would be as minimal as possible. So this will tell me that I have the smallest number of chains to begin with. Okay, so that's my maximum flow side. I'm going to look at the minimum cut, and I'm going to relate that to the size of the antichain. So, how would we compute the size of the largest antichain? Well, the first thing we're going to do is we're going to consider just a regular cut, just a random cut. And we're going to look at all of the vertices such that P minus is on one side and P plus is on another side. And we're going to call all of the elements inside of the set A. Notice that if we have this sort of relation happening here, then, well, if A minus and B plus had an edge to begin with, then S and T would have been connected, right? Because I can go from S to A minus to B plus to T. So if I take any 2 points in A, and A minus and B plus happen to have an edge, that means S and T would have been connected, and therefore the S and T partition would not have been a valid cut to begin with. So that means there can't be any edge between A minus and B plus. In other words, if you take any 2 points in A, they are incomparable to begin with. Now, if I look at the minimum cut, the only edges that ever really contribute to my minimum cut happen to be all of the edges such that S and A minus forms an edge in my flow network, and A plus to T also forms an edge. So if I look at a cut, say, if I look at this cut here, notice that all of the elements inside of A can't actually, or the edges along A can't actually be part of my actual minimum cut. So the minimum cut happens to be, a cut happens to be P minus A. So we exclude all of the points that are inside A because those will never contribute towards my actual minimum cut. Right? Otherwise, there has to be an edge from, say, A minus to some other point B plus, and then to T. And therefore, that would not have been a cut to begin. In other words, the size of my anti-chain is going to be the size of P minus the cut. So if I have a minimum cut then A would be as large as possible. So let's sort of look at these things together. Okay, this isn't all this slide. So the maximum flow itself corresponds to P minus B, which is the number of partitions of my, well, it's the number of chains that form my partition. So that means B will have to be minimized, right? So the number of chains will have to be minimized. But the minimum cut itself corresponds to P minus the size of my anti-chain. And as a result, the size of my anti-chain has to be maximized because, well, the minimum cut will be as minimal as possible. And so if you put them together, that means the minimum number of chains that partition my partially ordered set corresponds to the size, the size of the largest anti-chain in my partially ordered set. So you can kind of see that the maximum flow and the minimum cut plays a huge role in proving Dilworth's theorems. Does anyone have any questions?
What's P again?
So P is my original set. So it's the set that I consider at the start. It's my partially ordered set, right? So it's basically the left-hand side. So it's all of the elements in my left-hand side. Yeah. Does anyone have any other questions about this theorem or the previous theorem? Thank you. So, in conclusion, the largest size anti-chain corresponds to the smallest number of chains that completely partition, and that's Dilworth's theorem.
And the chains need to be disjoint, right?
Yes, so that they will be disjoint.
Okay.
Any other questions? Cool. And we're going to look at the last theorem. So this theorem is a little bit easier because we sort of already have a graph to begin with. So in this problem, we are given a directed graph, not necessarily weighted, and we have two vertices in V, and these two are going to be non-adjacent. The question we want to ask here is, well, how many edge disjoint paths can I have from U to V? Well, if I look at this graph here, so if I have a look at this graph here, one possible path would be U to the upper vertex to V. Another one could be, I take the lower path, and another one could be, well, I take the middle path. So it seems like there are three edge disjoint paths from U to V. So if we have a look at this graph here, though, what do we notice? Well, another way to kind of think about this is each of the paths that I take has to correspond to some sort of UV path from U to V. And if I want to find the number of edge disjoint paths, then what that corresponds to, well, the minimum number of vertices I really have to, well, the minimum number of edges I have to cut so that U and V are completely separated, right? Because if I completely cut one of the edges, then there is no more path from U to V via that particular path. So if I can find the smallest number of paths that I can cut, or smallest number of edges I can cut that completely separate U and V, that corresponds to each of the separate paths that I can take from U to V. And that will tell me the number of edge disjoint paths from U to V. And this is exactly what Menger's theorem tells me. So if I have two vertices, U and V, then there is a UV separating set of edges, let's call it S, and a collection of edge disjoint paths such that the number of edge disjoint paths from U to V corresponds to the number of edges that I have to remove such that U and V are completely separated. And you can kind of see that this is pretty much just maximum flow min cut, right? You cut along the edges, and that will tell you the number of paths that is required, or the number of paths possible from U to V. So, the way that we're going to construct this is U and V are going to be my source and sink. Each of my edges are going to have capacity 1. And notice that if we do it this way, then no two UV paths can ever share an edge. Why is that? Well, if they did share an edge, there must have been some vertex that has a capacity 2. And if it has capacity 2, then either you're going to separate to two completely different paths, or you're only going to flow one unit of flow down one particular path. And so therefore, if you take any two UV paths, you can't ever share an edge because you can't ever have a flow of 2 along that edge. And because each of the edges have capacity 1, this will tell me that a cut basically counts the number of edges that pass through the cut, and therefore the minimum cut has to correspond to the number of paths I can take from U to V. But because each of the paths are edge disjoint, that means these are going to count as the number of edge disjoint paths from U to V. Yeah. And you can kind of see that by applying maximum flow, that will tell you the number of, or the smallest number of edges I want to remove so that U and V are completely separated. And then because of that, you can count the number of edge disjoint paths from U to V. Are there any questions on this? So those are sort of the 3 main theorems for today's talk. There are some other theorems that have applications to maximum flow. There's Koenig's theorem, which deals with maximal matching. There's also Mirsky's theorem, which is the dual of Dilworth's theorem. So notice that in Dilworth's theorem, we said that the size, the larger size of an anti-chain corresponds to the minimum number of chains in my partially ordered set. Turns out the dual is also true. So if you take the largest chain of my partially ordered set, that corresponds to the smallest number of anti-chains along my partially ordered set. And that's exactly Mercer's theorem. And there's also a generalization of Dilworth's theorem. So instead of taking just independent set, we want to take a union of independent sets, and it turns out this is Brigham's theorem. So that's basically all of the theorems that we have for today's talk. Before we wrap up, does anyone have any questions on this? If not, then thank you for coming, and I hope you've learned something valuable or something interesting from today's talk.